Hello, welcome to Q in Motion, Understanding Electricity. This is our first class for the Understanding Electricity course. Okay, so today we're going to talk about several concepts that are used in electricity and electronics, right? Charge, current, unit prefixes, voltage, what is ground, and we're going to talk a bit about how to measure voltage and current. So first of all, what is electric charge? Well, if we recall, matter is made up of atoms, right? So atoms have a nucleus in the middle, right, with protons, and those have positive charge. Now, around the protons in the nucleus, we have electrons, which have negative charge and are kind of spinning around the nucleus, right? So the charge, we symbolize that with the letter Q, lowercase q, and it's measured in a unit that is called coulombs, and that is symbolized with a capital C. Okay, so let's see what happens when we connect a battery to a piece of wire. Let's assume it's copper, right? So in a battery, we have a negative terminal, which is a place in the battery that has an excess of electrons. And we connect that to that metal wire that has the same number of protons and electrons. So it does not have a net charge. You have positive and negative charge and they cancel each other. But the important thing here is that the electrons are free to move within the metal. We sometimes call these a sea of electrons, right? Imagine the nucleus of the atoms of copper fixed in the structure of the copper, and the electrons free to move around, okay? And then we have the other terminal of the battery, which is called the positive terminal, which has a lack of electrons. So it has less electrons than protons, so that has a positive charge. So when we do this, we provide a path for the electrons in the negative terminal to travel through the copper. Remember, the electrons are free to move through the copper and then go back to the positive terminal, right? So this movement of charge is what we call electric current. So let's talk a bit about electron flow versus current flow. So the way we described the previous slide was electrons flowing from the negative terminal to the positive terminal. As a convention, current flow is defined as if positive charge was moving from the positive terminal to the negative terminal. So if you have a look at this drawing, right, the electron flow is from the negative terminal to the positive terminal. But we don't really talk about electron flow, although that's what's happening at an atomic or subatomic level. So from a macroscopic level, we consider that positive charge is moving from the positive terminal all the way to the negative terminal. And that is what we call current flow, or simply current or electric current. Remember, current flows from the positive terminal to the negative terminal. So electric current is a measure of how much charge is moved per second. And we will symbolize that with the letter I. So I is the current intensity, or just simply we will call that current. We will see some equations next class that will involve the value of the current, and that's going to be symbolized with a capital letter I. Current is measured in amperes or amps, and the symbol for the unit itself, it's going to be an A, a capital letter A. 1 ampere is 1 coulomb per second. Remember that current is a measure of charge moved per second, and charge is moved in coulombs. So 1 coulomb per second is 1 amp. So because we cannot see electric current, it is very useful to make an analogy with something that we can see. And because many of the equations that govern electric current are similar to the equations that govern water flowing through a pipe, we can make this analogy between current and water, right? So electric current is charge flowing through a conductor, and that is going to be similar to water flowing through a pipe. Okay, so here we have something that we can all relate to a lot more than electricity, probably. So we have here a reservoir, a tank filled with water, and at the bottom of the tank we have a pipe. And we know from experience that in this situation, the water from the tank is going to flow through the pipe and spill on the floor, right? So that water flowing through this pipe is similar or analogous to the current flowing through a conductor. Before we move ahead with the next topic, we will be reviewing the prefixes, some prefixes for units greater than 1. For instance, we have kilo, which is 1,000 or 10 to the cube. So an example of how we would use this is in a kilometer. A kilometer is 1,000 meters. So instead of saying 1,000 meter, we said 1 kilometer. Another one is mega. So mega is 1 million or 10 to the 6. An example of this would be megohm, which is 1,000,000 ohms. We're going to see in next class what an ohm is. If we keep going up, we will get to giga, which is 10 to the 9. And an example of this would be gigabytes. So a gigabyte would be 10 to the 9 bytes, and that is a lot of bytes. The same way we have prefixes for units that are more than 1. We have prefixes for units when the number is less than 1. In this case, we have milli, which is symbolized with a lowercase m, which is 1,000. And an example of this could be a millivolt. So that would be 1,000th of a volt. A micro, which is 1 millionth, and it's symbolized with the Greek letter mu. That is an example for this could be a microamp, right? Or a microampere. If we keep going further down, we have nano, which is 10 to the negative 9. And that is symbolized with the lowercase letter n. An example of these could be a nanometer. What is a nanometer? Well, it's a very tiny unit of measure, right? When you get into semiconductor fabrication and the devices that are inside a computer chip, you will get into ranges, distance ranges or size ranges in the nanometer range. Even lower than that is a pico, symbolized with the letter P, a lowercase p, and that is 10 to the negative 12. On another class, when we start looking at capacitors, we will see that pico is a prefix that is used many times for capacitors. For instance, a picofarad. Okay, so that's tiny units of capacitance. Okay, so going back to electricity, let's see what are some typical values for electric current. So if we have a battery operated device like a clock or a remote control when not transmitting, think of devices that are battery powered and do not have an on-off switch, and the batteries last several months. So in those cases, the current being taken by those devices is around 1 microamp or even less sometimes. If we have an LED indicator, like a little red or blue LED that indicates that the power is on, that's going to be taking around 10 to 20 milliamps. An incandescent lamp of 60 watts, 120 volts, that's going to be 0.5 amps. A wiper motor in a car, it's going to be in the vicinity of 2 to 3 amps. And a starter motor in a car is going to be like 100 amps. So as you can see, the range of values for electric current, even in daily life, right? We're not even getting into power distribution or industrial values. So that even in our houses or cars, that is ranging from like microamp or less to 100 amps. So the range of electrical current that we can find, it's varies a lot. So now would be a good time for you to take a break if you want. So you may want to hit pause and take a 5-minute break before we continue with our next topic, that it's going to be voltage. Okay, I hope you enjoyed your break. Let's now talk a little bit about voltage. So if we go to the physics book, we'll see some definition, something like this, right? So the amount of work, of physical work, that it takes to move a charge of 1 coulomb from point A to point B. The problem with this definition of a volt or voltage is that it is not very useful to gain an intuitive understanding of what voltage is. And that is the aim or the goal of this class. So, but one thing that we have to pay attention in the original definition of voltage is that it refers to point A and point B, right? So whenever we measure voltage, it's going to be measured between the points A and B. So we always have to define which 2 points we are referring to when we measure voltage. So if we want to try to gain a more intuitive definition or a more intuitive knowledge of what voltage is, think about it as the amount of force available to move charge from point A to point B, okay? In same way we did an analogy between water flow through a pipe and an electric current, we can make an analogy with water for voltage. So voltage in a water analogy is similar to water pressure. If we look at this diagram here, we have a water reservoir, the same tank we used to have, only now, and the same pipe, only we blocked that pipe so water is not flowing. And we put a pressure meter here. So this thing is gonna be measuring the pressure. So in this case, you're gonna have water pressure here in the pipe without current flowing or without water flowing, right? So there's no need to have current flow in order to have voltage. In the analogy of water, the water pressure is gonna set by the level of water in the tank. If you have a higher level of water, that's going to be more pressure. And if you have a lower level of water, let's say at this level, you will have less pressure. If you open the pipe and let water flow through the pipe, the more, and this is something it's easy for us to see because we have experienced it somehow, right? So the higher the level of water that we have in the tank, the higher the pressure and the more water you're going to have flowing here. So kind of the same happens in electricity. So the higher the pressure or the higher the voltage, the higher the current, assuming everything else stays the same. Okay, so we're going to leave it like that. We're not going to try to define voltage anymore, but think of it as the amount of force that is available to move charge through a circuit, right? The same way in the water analogy, it would be the amount of force available to move water through the pipes. Now going back to the fact that voltage is measured between the 2 points, we have to specify what those 2 points are, right? So the notation that we're going to be using is this one, VAB. So VAB is the voltage between points A and B. So let's consider this circuit, doesn't matter what's inside, right? And let's say we have 2 points of the circuit. One point is A and the other one point is B. And it happens to be that A is more positive than B, right? So, And let's assume the voltage between points A and B is 5 volts. So we say VAB, right? So this is how we denote the voltage between points A and B is 5 volts. Now, the voltage between points B and A is negative 5 volts. So how does this happen? So it's just a convention. So if we say VAB is positive, it means that point A is positive and point B is negative. So if VBA is negative, it means that point B is negative compared to point A, and point A would be the positive. So these two expressions are exactly the same. Let's have a look at what kind of voltages we can encounter in real life. So if we go to ECG or EKG, as it's sometimes called, it's the electrocardiogram, and this is a way of monitoring the heart activity measured on the skin, right? The electrical activity of the heart measured on the skin. You would be measuring voltages close to 1 millivolt. If you measure a AA battery or a AAA battery, that would be 1.5 volts. A car battery would be 12 volts. Household outlet would be 120 volts or 220 volts or 240 volts, depending on where in the world you are, right? Depending on the countries. Some different countries have different standards for household outlet voltages. If you go to industrial machineries, you can have 380 volts, 480 volts, and 660 volts, again, depending on where in the world you are. And if you go to the distribution voltages from a power plant, you can have up to 735 kilovolts. And this may be changing with time. And as power plants go to higher voltage, that will result in better efficiencies. So if you notice this last three lines, I put those in red. So be careful with those voltages because these could kill you. Usually up to 48 volts, it's considered safe. You can touch those without any problems. Once you go above 48 volts, you should not touch those conductors directly. And I'm touching with your skin. I'm talking about your skin, your fingers, right? If you have exposed tissue, even these lower voltages could be lethal. But under normal circumstances, you can touch a car battery, no problem. You can stick your finger in the outlet for the cigarette lighter in a car. It will have 12 volts, but nothing's going to happen to you. But don't do that with your household outlets or anything higher than that, okay? Now, let's talk about ground. What is ground? So I've been mentioning that voltage is measured between 2 points, right? So A and B. But many times it is convenient to define a reference point and measure all the voltages against that reference point, right? And this reference point is, it's going to call ground. And it is often, but not always, the negative terminal of your battery, if it is a battery operated device. Now, this is just a convention. It could be anywhere in the circuit, really. The advantage of using the negative terminal of the battery is that all the voltages are going to be positive, right? So it is easier because you're not going to be having positive and negative voltages. It's only positive voltages. It makes all the analysis a lot easier if you connect it to the negative terminal of the battery. Let's talk about ground and how that can be used in an example in a circuit. So here we have a circuit with a battery, a device A, and device B, and a device C. And down here we have the ground, right? This is the ground, the symbol for ground. And as we can see, it is connected to the negative terminal of the battery, okay? So by definition, ground voltage is 0 volts because every voltage in the circuit is referred to ground, right? and the voltage from ground to ground is 0, right? All the rest of the voltages are referred to this ground. So if we identify these nodes as A, B, C, and D, these different points in the circuit, we have VA is 1.5 volts, VB, or the voltage at B, is 1 volt, and VC is 0.3 volts, the voltage at node C. Like we said, the voltage at node D, which is ground, is 0 volts. So have a look at this. We refer to this one as VA and not VAB or anything like that, because we understand that the voltage, this is a voltage on point A, but referred to ground. So this 1.5 volts referred to ground. VB is 1 volt referred to ground, and VC is 0.3 volts referred to ground. Once we have all these voltages referred to ground, we can calculate the voltages between two different points, right? So the voltage between point A and B, it's going to be the 1.5 minus the 1 volt. So that's going to be 0.5 volts. VAB, or the voltage on device A, it's going to be 0.5 volts. The same way we can calculate the voltage across device B, which would be VBC, right? And it's going to be 1 volt minus 0.3 volts, and that's going to be the 0.7 volts that we have here. And VCD, it's a voltage across device C, it's going to be 0.3 volts, which is the voltage at point C, minus the voltage at point D, which is ground, so the voltage at point D is 0. So VCD is going to be 0.3 volts. Now, this is not the only ground that you're going to see, the only symbol that you're going to see for ground. There are other symbols that are commonly used to signal ground. So this one, and this one are other symbols that you may see to symbolize ground. So let's have a look at how we measure voltage. So voltage is measured with a voltmeter, which is a function included in a multimeter, right? If you have a multimeter, you have a position in your main function selection knob that is going to be voltage measurement, right? So that's going to be working as a voltmeter. If the positive terminal of the meter is connected to the more positive point, the reading will be positive, otherwise it will be negative. Let's have a look with a quick example here. So let's go back to the same circuit. We have the negative terminal of the battery connected to ground, and then we have our device C, and as you recall from the previous example, we had 0.3 volts here. So if we want to measure this voltage, we connect a voltmeter here and here, the positive terminal here and the negative terminal here. And the voltage reading is going to be 0.3, right? Which is the 0.3 volts that we have here. Now, if we connect the voltmeter the opposite way with the positive terminal of the voltmeter to the negative terminal of the device C, and the negative terminal of the voltmeter to the positive terminal, the voltage reading is going to be negative. It's going to be minus 0.3. Okay, so if you measure the voltage on a device like this and you obtain a reading of a negative voltage, that really means that the voltage is 0.3, but this one is positive and this one is negative. Okay. Now, how do we measure current? Let's recall that current is flow of charge. So to measure current, we have to open the circuit and make the flow of charge go through the instrument that we're going to be using. The instrument is going to be an ammeter. And so the current is going to flow through the ammeter and through the rest of the circuit as well. So going back to our example here, we have a battery, device A, B, and C. And let's assume we want to measure the current flowing through this wire here. Okay, so the first thing we do is open the circuit. We have to open the circuit and cut the circuit so that there's no no current's going to be flowing here. And once we open the circuit, we connect the ammeter. So the current flow is going to be from the positive side of the battery through device A, device B, the ammeter, and then through device C and to ground or to the negative terminal. And we will have a reading here, say 12 milliamps, okay? So the same happens with the polarity here. So if current enters the ammeter through the positive side and leaves through the negative side, your reading is going to be positive. Otherwise, it's going to be negative. So that would be all for today's class, right? But let's remember what topics we went through today. So current is a flow of charge per second, and it's similar to flow of water through a pipe, right? So keep that that image in your mind. We will get back to it next class. Current is measured in amps or amperes, and its symbol is an A, right? The symbol for current is I, but the symbol for the amps is A. Now, to measure current, we have to open the circuit and insert an ammeter, which is what we just saw in this previous slide. Then we started to look into voltage, right? So voltage is similar to water pressure and can be thought as the force available to move charge from a point A to a point B. And it is measured in volts. To measure voltage, measuring voltage is always a lot easier than measuring current. So you don't have to open the circuit, you don't have to modify the circuit. We just connect the voltmeter between points A and B, and you just measure the voltage. And this concludes our first class. And on our next class, we will be covering electric power, electron resistance, and Ohm's law. So I hope you enjoyed this. I hope this was useful for you to understand a little bit more of electricity and as we get into electronics and try to understand how all of these invisible atoms and electrons and protons work in a circuit. Thank you.